Now we will get into the functional groups which contain nitrogen. This consists of the amines and the amides. So we will start with amines. Amines are compounds that contain at least one bond between carbon and nitrogen. We divide these into three categories, much like we did with alcohols and with some of the other functional groups, like, for example, alkyl halides, although you'll see there's a big difference. And we divide them as so. Primary amines have a bond between carbon and nitrogen with two hydrogen atoms. Secondary amines have nitrogens bonded to two carbon atoms and one hydrogen atom. And tertiary amines has a nitrogen bonded to three different carbon atoms, and importantly, it has no hydrogen atoms. And in all of these compounds, the nitrogen atom also has a lone pair. Now this is different from the other functional groups that had this primary, secondary, tertiary system, because we're not looking at the carbon and how many bonds it's making to carbons, but the nitrogen and how many bonds it's making to carbons. So that is a difference. So here are three generic amines that we're going to kind of show here with R groups. So this would be a generic primary amine, where the R could be a methyl, an ethyl, or any other such group. Here we're showing two carbon groups bonded to the nitrogen. And then here we are showing three groups bonded to the nitrogen. So now let's, as we're going to get into the properties, we want to look at the shapes and some other features of the molecule. So what is the shape about nitrogen in all three cases? Probably easiest to see with the secondary and the tertiary amines here, but we have a lone pair on the nitrogen, and the nitrogen is bonded to three different atoms. That's the same for all of these. So what kind of a shape is that? You'll recall that's called trigonal pyramid or trigonal pyramidal. And you'll remember that the bond angles around those are about 109.5, just like tetrahedrals. Can primary amines hydrogen bond with each other? Remember, to hydrogen bond, you need two components. You need a hydrogen bonded to fluorine, oxygen, or nitrogen. Well, we have two hydrogens bonded to nitrogen here. And you also need a fluorine, oxygen, or nitrogen with a lone pair, and this certainly does. And so, therefore, yes, primary amines can definitely form hydrogen bonds. Secondary amines also can form hydrogen bonds with each other. They have both parts, the hydrogen bonded to nitrogen and the nitrogen with a lone pair. Tertiary amines, on the other hand, cannot form hydrogen bonds with each other because none of the hydrogens are bonded to nitrogen in this structure. They're all bonded to carbons, or it's implied with these R groups. So they cannot hydrogen bond with one another, tertiary amines with each other. So what does that tell us about their melting and boiling points? As we saw earlier, in general, if we were to compare molecules that have similar molecular weights, the primary and the secondary amines should have fairly high melting and boiling points because of their ability to hydrogen bond with one another. That's not going to be as much the case with tertiary amines. With tertiary amines, their strongest intermolecular force is going to be, think about this, nitrogen bonded to carbons. Nitrogen is more electronegative, so it's going to be a dipole-dipole force. And so their melting and boiling points aren't going to generally be quite as high as those of other groups. How about this question? Are they likely to be soluble in water? So getting back to the most important point when we talk about solubility is like dissolves like. Amines, if they are able to form hydrogen bonds, are going to be very likely to be soluble in water, at least small amines. So I would definitely expect primary amines with no more than about 4 or 5 carbons to be soluble in water. Secondary amines, if they have, again, probably no more than 4 to 5 carbons, should be soluble in water. Tertiary amines should be reasonably soluble because they do have dipole-dipole forces, and this lone pair is able to hydrogen bond with the hydrogens of water. However, I would generally expect it to be somewhat less soluble than for the other two groups. Amines tend to be among the most unpleasant of all of the functional groups in terms of smells, and generally are very unpleasant to work with in many circumstances. To give you some extreme examples, some diamines, those would be compounds that have two NH2 groups, are known for very unpleasant smells, and these include, for example, the smells of rotting animal flesh, including especially fish flesh, and those would be putrescine and the very aptly named cadaverine. And we also find amines contributing their smells to different biological fluids that we might encounter, and decomposition of animals and bacteria and all kinds of other things. So these all, again, generally don't smell nice. I'm sure I could find an example that would be the exception to this, but when we think of amines, we don't usually think of good smells. For amines, I'm going to follow the book's lead and only ask you to learn a few common names for these. So to name the amines, we're going to have a slightly different system here for these guys. You identify all the alkyl groups bonded to the nitrogen, so methyls, ethyls, isopropyls, propyls, etc. You then list those groups alphabetically, and then you add the word amine at the end. If you have two of the same group, like two methyls, you would use the prefix di. So dimethylamine, for example, would mean that there's two methyls on a nitrogen. And if we have three of the same group, we would use tri. The book does talk about naming anilines. However, I'm not going to be concerned with that. Those would be aromatic amines. So let's take a look at a few amines here and determine if they're primary, secondary, or tertiary, and then we want to name them. So here we have a nitrogen. It is bonded to one carbon, so that is going to make it primary. We could also look at the hydrogens, although that's less easy. If it's bonded to one carbon, it will have two hydrogens. There's also a lone pair, although I've elected not to show it here. Okay, so this is only going to be bonded to one carbon group. This is an ethyl group. So we just list that carbon group, and then we add the word amine. So ethylamine. How about this nitrogen? It's bonded to three carbons, so it is a tertiary amine. What groups does it have? Methyl, methyl. Okay, so two methyls. So that's dimethyl, and then ethyl. We list these in alphabetical order. E for ethyl comes before M for methyl. We don't include D for dimethyl. This is considered methyls. So the name of this compound is going to be ethyl dimethylamine. And then this nitrogen here is bonded to a carbon, another carbon, and a hydrogen, so it is a secondary amine. And what groups is it bonded to? Well, we've got a methyl, and we have here, there's three carbons, and the nitrogen is attached at the middle, so this is an isopropyl group. So alphabetically in order, we have isopropyl and then methyl. So isopropyl methylamine. Notice no spaces in these names. Just as carboxylic acids were the most acidic of the functional groups in general, we find that amines are the most basic. And that should kind of make sense to us. Even if we think of the name amine, it's very closely associated with the base ammonia. As bases, this means they will accept a proton, that is an H+, and form ammonium salts when they are reacted with acids. So here we have an example of that reaction. This is ethylamine, and this is hydrochloric acid. So the lone pair is going to take the hydrogen, and then that leaves over the chloride as Cl-. So this now has a plus charge, the whole unit. Some people will write brackets around this, and that's fine. we're not going to worry about naming of ammonium salts. So this is an important observation that I'd like you to make here. We've said that nitrogen generally makes 3 bonds and has 1 lone pair. This nitrogen is making 4 bonds and has no lone pair. And we see that whenever we have an ion, at least one of the atoms in a molecule is likely to not follow the usual charges. And that's what we see here. This nitrogen is making 4 bonds. We also saw that earlier with the carboxylic acid salts. We had O-. In those cases, oxygen, instead of making 2 bonds, was making only 1 bond and has 3 lone pairs. So whenever we have an ion on an organic molecule, it's going to be unlikely to follow the standard bonding rules for at least one atom, usually nitrogen or oxygen or sulfur. Here's another example of a reaction to form an ammonium salt. We have here a tertiary amine. This is trimethylamine, again with hydrochloric acid. So the lone pairs are going to take that hydrogen away, and essentially those lone pairs are now making this new bond with hydrogen. So we call this whole thing here an ammonium salt. The positive charge is technically said to reside on the nitrogen, but we're not going to get that into detail. So I'll just follow the book's example and keep it in a square bracket with a positive charge on the outside. Chloride is now an ion, and so it remains outside of these brackets here to show that we have essentially an ionic attraction. A good question to ask right now. We saw that amines are generally pretty soluble in water, especially primary and secondary ones. Is this ammonium salt going to be more or less soluble? In general, ions are quite soluble in water. They are probably going to be more soluble than almost any other group that we look at in terms of organics. And so we would strongly expect that ammonium salts should be more soluble in water, just like carboxylate salts were more soluble in water. And now we're going to cover our last functional group, and that is going to be amides. So, as you might assume, since there's only a 1-letter difference between amines and amides, there are definitely going to be similarities, the major similarity being that they both contain carbon-nitrogen bonds. But the big difference here is with amides, just like carboxylic acids, there is also a double bond between that carbon and oxygen. So let's look at a few examples into the way that we're going to categorize them and what they look like. First of all, we can categorize amides as primary, secondary, or tertiary in exactly the same fashion as amines. We look at the nitrogen and we see how many carbons it's bonded to. In this case, it's bonded to 1 carbon, and since that carbon also has a double bond oxygen, that makes this an amide. These are the atoms that you're looking for, these 3 here. So since it's only bonded to 1 carbon, this would be a primary amide. This nitrogen is bonded to a carbon here, and this R group stands for some carbon, so it is a secondary amide. And we also notice it has 1 hydrogen. And then nitrogen here is bonded to 3 carbons, and so that's going to make this a tertiary amide. The naming system for amides is essentially the same as for carboxylic acids, with the exception that instead of ending in ic acid, we're not going to be very creative here. We're going to end in amide. That's all there is to it. There is one additional change that occurs for both amines and amides, but we're only going to look at this issue for amides, and that is when we have substituents bonded to a nitrogen, instead of numbering like we would normally do with substituents, we put the letter N in front of that substituent. Now obviously we're assuming that the compound only has 1 nitrogen. If there's more than 1 nitrogen, that would make this very challenging, and I won't ask compounds where that's the case. Okay, so it's best as always to look at the acid that this would have come from. So when we look at this guy here, if this was OH, this would have been acetic acid, right? So we change the ending from ic acid to amide. This is just acetamide. How about here? So again, this would be coming from an OH group here. This would be benzoic acid. So if these were both hydrogens, that would have been benzamide. However, we have a methyl group on the nitrogen, and this is where that N naming comes into play. So we're going to say N-methyl benzamide. Now you might say, well, why do we have to say N? Well, because what's to say the methyl wasn't on some other part of the molecule? Like, for example, particularly in this next molecule over here, what if there was a methyl right there? Well, we would have to come up with a number for that. So N is kind of acting as a placeholder in a way that a number would. Okay, let us look at this final compound here. Again, if we think of this as being like a carboxylic acid with an OH right there, that would have been 1, 2, 3, 4 carbons. That would have been butane or butanoic acid. So it's going to end in butanamide. And we have two groups on the nitrogen here, and they are both ethyls. So we're going to say, just like if we were numbers, we would say N, N, diethyl butanamide. So two ethyls on the amide derived from butanoic acid. Now, when we look at amides, we find that there are some similarities between amides and the very closely related amines, although there will be one very big difference that we'll see in a moment. So both of these types of compounds can form hydrogen bonds, although we run into the same problem with tertiary amides that we did with tertiary amines. They cannot hydrogen bond with other tertiary amides, and so therefore we would expect them to have slightly lower melting points and boiling points than the other types of amides. So we would expect primary amides and secondary amides in particular to have fairly high boiling and melting points compared to other compounds. However, they are generally not going to be as high, and this is true for amines, as, say, alcohols and carboxylic acids. The carboxylic acids tend to have the highest boiling and melting points of all the organic compounds, as well as than the alcohols, because the oxygens have two lone pairs. Nitrogen only has one lone pair and therefore engages in less hydrogen bonding. So definitely higher boiling and melting points than most groups, but not usually quite as high as alcohols and carboxylic acids with their oxygens. Small amides are generally going to be soluble in water because they can form hydrogen bonds with water, primary, secondary, and tertiary. Now here is the very big important difference between amides and amines, and I don't want you to think I'm just leaving out reactions. Amides are not bases, so we don't see common reactions with amides becoming ammonium salts. That reaction is definitely not going to be common amongst amides. And in fact, amides are going to be more similar to esters than probably any other group in terms of the way they are going to react. So we can undergo hydrolysis, just like esters. Remember, with esters, hydrolysis meant ester plus water in an acid. So same thing here, amide plus water in an acid. And when we combine an amide and water, this will produce a carboxylic acid, and originally it will form an amine, but because amines are basic, they will also react with the acid to form an ammonium salt. And we're typically going to use hydrochloric acid in this case. So let's see if we can pick out exactly what's going on here. So I've color-coded several atoms. So first of all, in our amide, we have this is a secondary amide. We have a nitrogen here to 2 carbons. It's going to pick up a hydrogen from water and a hydrogen from the acid to form the salt over here. And then the OH group will join onto the carbon. So again, very, very similar to what we saw with esters. We just, oops, let's change that pen. We're just going to take these guys off. And that would be our amine. But then we get another hydrogen from the hydrochloric acid. And then the OH can go right there. So these two groups right here are essentially substituting for each other. And as esters could undergo hydrolysis in base, so can amides. So if we add an amide and water in the presence of sodium hydroxide or potassium hydroxide, it will produce the carboxylic acid salt and an amine. Or it could produce ammonia if we had a primary amide. So let's look at an example here. So we go ahead and we identify our groups that are going to come off, just like we did for esters. Okay. And then the OH would attach here. But again, it's not OH, it's O-. And that's because, even though this is an acid, it forms a carboxylic acid, this is a base, and so it would immediately take away any hydrogen that was on the carboxylic acid. Again, we saw that reaction in the previous video lecture, the reaction between a carboxylic acid and a hydroxide, a base. Nature is rich in amines, and many of these amines have very important physiological properties. We call these complex, naturally occurring amines alkaloids. Alkaloid or alkali means basic, and we know that amines are basic, so that's where the term is derived from. So to give some examples of some of the more famous alkaloids that are out there, we know the painkiller morphine is an alkaloid. Caffeine, which is a stimulant, along with ephedrine, and nicotine, which of course is found in tobacco. These compounds can be taken away from natural sources, isolated from them, typically plants, usually by treating them with an acid, and usually we use hydrochloric acid for this. So, for example, to isolate caffeine, we could get that from a natural source, usually by treating with hydrochloric acid. Morphine, definitely that's going to be the case by treating poppy with acid to recover the morphine. And what we call those specific salts, they're ammonium salts, but since we used hydrochloric acid, we usually call them hydrochloride salts. But you'd be fine in calling it an ammonium salt. And they're usually water-soluble and easily dissolved in the acid, and that makes them recoverable. So, possibly not the best example, because I don't want you to encourage you to do this example, but if one were to want to recover cocaine, cocaine can be derived from the coca plant, which you probably do not have access to. I'm certainly illegal in this country. But by basically taking the parts of the plant which contain the cocaine, you can crush those up and add hydrochloric acid. And why would we want to do that? Well, hopefully you wouldn't want to do this, but let's say you did. Let's look at the different functional groups that we have in cocaine. Well, we've got an aromatic here. We've got an ester. We have another ester. And then we have an amine. This is a tertiary amine. And it's got this carbon bridge across it right there. What is that going to do? It'll react with hydrochloric acid to form an ammonium salt. It's taking that hydrogen. Why would we do that? Remember, ions are generally going to be much more soluble in water than the compounds they're derived from. Look at this compound. Lots of carbons, some groups with dipole-dipole moments, but dipole-dipole forces, excuse me, but not much that's going to make it soluble in water. And so by adding hydrochloric acid, we change it to an ion and easily make it removed. And when one talks about the illegal drug cocaine, the type of cocaine that is typically inhaled, they're talking about this, cocaine hydrochloride. Now, cocaine hydrochloride, when added to a base, in this case, this is just baking soda, sodium bicarbonate, can lose that hydrogen again. And that takes us from cocaine hydrochloride, the type which is, again, typically snorted and sometimes used for medicinal purposes, into the much more dangerous crack cocaine, which is also sometimes called freebase. Freebase meaning it is a base, again, here. You'll notice this is a rather impure sample owing to its color. Normally we would expect a lot of pure organics to have a white color. That's certainly not going to be true of all organics. But what is going to be the problem with this? Well, there's a number of them, but one of the problems is, since this is less likely to be soluble in water, it's more likely to be soluble in fat, and is more likely ultimately to persist in the body, making it a problem that isn't of just a short-term issue like cocaine, but a long-term issue that stays with us. This brings our lectures on organic chemistry to a close. When we start up again with Chapter 14, we're going to be looking at carbohydrates, which will take a lot of the organic chemistry that we've studied up until this point and put it in a biological context. Thank you.